We've seen that organic molecules can get very complex. We can have carbon chains longer than we can count. We can have them attached to cycloalkanes on every individual point. We can have hundreds of carbons all connected together with 200 hydrogens connected in place. There are great layers of complexity in organic chemistry and with organic molecules. A lot of that complexity won't just come from the fact that we can have giant molecules that can loop around each other, but it'll actually come from the fact that these molecules can have the same number of atoms, the exact same number of carbons and hydrogens in a carbon chain, but be connected in different ways. We call this concept isomerism. Isomerism is molecules with the same chemical formula with different connections. And we've already seen this a little bit. We haven't named it this way, but we have seen it. The constitutional isomer, also known as a structural isomer, is simply when we have something like a carbon chain that has physically different connections. So what I have here is a 9-long carbon chain. This would be nonane. We can look at this. Nonane would be 1, 2, 3, 4, 5, 6, 7, 8, 9. Now, nonane has the chemical formula C9H20. There are 20 hydrogens on this. There are 9 carbons. At any point along this carbon chain, I could take out a hydrogen, pull off my end carbon, and I can attach it as a methyl group. I have the exact same number of elements in this molecule, but it is now slightly different. This has gone from nonane to 4, 5, 6, 7, 8. 1, 2, 3, 4, 5. 1, 2, 3, 4. 4 methyl octane. And this chemical formula remains unchanged. C9H20. H2O, H20. There we go. I can do it again. So I can just take a hydrogen right here, break it off, grab a methyl group from the end, stick it on, put my hydrogen back in on the end, and now I have a 7-long carbon chain with an ethyl group sticking out. I can even move this around and make it a little easier on myself. So we see this. I still have the same number of elements here. I've got 1, 2, 3, 4, 5, 6, 7, and then I am 1, 2, 3 in, 1, 2, 3. So this becomes 3-ethyl heptane. But it still has the same elements, C9H20. So this is a structural isomer. We give these different names. I could move this methyl group anywhere I want it. I could say, you know what, I'm going to move it a little bit further in and call it 2-methyl octane. 2-methyl octane and 4-methyl octane are structural isomers of one another, and we already know how to name them and how to identify them. Later on, we will actually look at what are some of the differences in structural isomers. A lot of it is going to have to do with how much steric hindrance there is, which is really to say how crowded a certain atom is. That's just a special name to say how crowded an atom is. We're going to see that it impacts bond energies and heats of combustion. There are a few different properties of elements, of compounds, that are adjusted by structural isomerism, even within the same functional groups. Even if I had an alcohol somewhere along this, moving the alcohol from here to here to here would change its structure. It would make it a different constitutional isomer. So let's define this. Let's define a constitutional isomer as an isomer with a physically different bonding structure. And let's look at one more example of that to see how extreme this difference can be sometimes. A cycloalkane's chemical formula is very easy to determine. It is simply going to be the number of carbons. The number of hydrogens will be twice that. So for each carbon, I'm going to have 2 hydrogens. So this is 1, 2, 3, 4, 5, 6. So cyclohexane is C6H12. Well, what is another hydrocarbon that has the formula C6H12? That's very different. Well, I can just turn this into a straight chain. Now, an alkane, its formula is very easy to find as well. It's always going to have 2 hydrogens for each carbon plus the 2 extra hydrogens at the end. It's going to be CnH2n plus 2. That's a simple way to find that formula. But if I just throw in 1 double bond, that'll remove 2 hydrogens, and now my chemical formula for this is hexene. Doesn't really matter where I put that double bond, it'll still end up with the formula C6H12. And now I have 2 very different molecules with very different properties that have the exact same chemical formula. If I burned them both, they would go through the exact same combustion reaction, but they would produce different amounts of heat. They're able to go through many other varied reactions, especially organic reactions, just by this structural difference. So structural isomerism is very important. But we don't have any special naming conventions that we haven't already talked about that will be referencing structural isomerism. We already know how to name all of these different isomers. We just find methyl groups and ethyl groups and alcohol functional groups. We find all of those things. We've got hexene, we've got cyclohexane. Those are distinct names. So we're already able to differentiate constitutional isomers. Okay? What we don't know how to do is how to deal with the other type of isomer, a stereoisomer. A stereoisomer is going to be a spatially different molecule. What does that mean? There's going to be 2 big instances where this comes up. But what's really going to happen here is we're going to have the same connections, but those connections might be flipped. So we're going to have the same molecules, same elements. We'll say the same elements. Let's use a different color. Same elements. Same bonding structure. But a different bonding symmetry. For our spatial isomers, there will be 2 types. One will be an optic isomer, the other will be a geometric isomer. Let's look at those 2. The 2 types of stereoisomers are known as enantiomers and diastereomer. These are challenging words to pronounce. The enantiomer will be the primary subject of the next unit, where we will discuss the concept called chirality. Chirality really references, these are new words, yes. Chirality really references whether or not something has a mirror image. And whether or not that mirror image is different. So a mirror image that is different. What do I mean by that? Well, the best example, the quickest example is just your hands. So if I look at this, if I just draw my hand up here, there's my hand. Great. It's set this way. Now, my hands are mirror images of each other, right? But if I take my right hand and place it over that image and draw it again, there's no overlap. It doesn't quite overlap correctly. It doesn't work. Now, that might seem nuanced and insignificant, but this is actually very significant when it comes to biochemistry. Our bodies and enzymes have specific receptors for specific chemicals, and medication has to fit those receptors perfectly. An example could be this molecule right here. I've got, in this order, I've got a chlorine, a bromine, and over here, a hydrogen. I might have an enzyme receptor that needs that exact combination of elements attaching to it in order to activate it. A medication might need to hit that receptor. Now, a medication that has an enantiomer would not be capable of fitting that. There's no way for me to arrange these so that I still hit that, because these two molecules are mirror images of each other. You can see that right there. See that? There's no possible way for these to overlap, and so they would have different chemical reactions. This becomes excruciatingly important, and one of the easiest ways to identify it is just the difference in the scent between an orange and a lemon. There is one difference between those two scents, and it is just that at one carbon, I get a hydrogen connected to the rest of the molecule, and on the other one, they're flipped. That's it. That is the only difference in limonene when it comes to an orange and a lemon, and they still get that different scent. So, that's all we're going to talk about enantiomers for now. We are going to get into them quite deeply in the next unit, but for now we need to talk about diastereomers. And I'm sure I'm not pronouncing that correctly. This is really the geometric isomer. This was our optical isomer, where just the way it looks shifts. There's a mirror image of it, and it will shift light, optical light, in different directions. But a diastereomer, this is going to be a geometric isomer. By geometric, what I mean is, even though molecules are going to be arranged in the same order, they're going to be stuck in a different orientation. This is going to come up with alkenes. So I've got ZE written up here. This is a reference to Zusammen Entigen naming convention. But a more common terms that are known for this are cis and trans. We're going to get more into this, so this is just an introduction. But what these molecules look like is if I have something, just a nice simple one, a butene, with my double bond on the middle carbon. If I've got it set up this way, these carbons are unable to rotate around each other. And so I can either have a butene that's set up this way, or this way. And these are not able to interchange. That double bond cannot rotate. And so let's look at an example. Here I've got the butane, this first butane, set up like this. my double bond is physically unable to rotate. These springs really work wonders replicating those pi bonds. But on the molecular level, I'm going to have a sigma bond between these two, and we're going to have a pi bond over the top of them. Those pi bonds are in a specific space, and they will lock that molecule in that orientation. And so I cannot move out of this orientation. My molecule is going to be arranged this way. I could have it arranged another way. I could, if that bond broke or formed differently, it could have formed this way. But again, it cannot break out of this conformation. These are stuck this way. So these two molecules, while connecting in the same way, with the same number of atoms, the same number of elements, both have 4 carbons and 10 hydrogens, or I'm sorry, 8 hydrogens. They're alkenes. But they are slightly different. This slight difference does impact its physical properties. On this level, it'll mostly impact its heat of combustion, its melting and boiling points. But this becomes very significant, especially when it comes to something like trans fat. Trans fat is a fat molecule that has been adjusted to switch from one of these orientations to the other. We're going to get into how to name these, cis and trans, Z and E, later. But when we get something from a saturated fat to a trans fat, it changes its melting point to be higher than your body temperature, which allows this fat to solidify in our veins. That becomes a huge problem. So just that small difference in how this thing is connected geometrically can have a significant impact on how it works in reactions and in a physical system. The second type of diastereomer that we're going to look at is the conformational diastereomer. Now this is, I'm going to bring back that nonane that we had before. I'm going to just break it down. So conformational isomer, let's pull this out right here. Notice, with just a simple alkane, these bonds, these sigma bonds, these are free to rotate. And on the atomic level, this is true as well. These bonds are freely able to rotate around each other, and they do. But right now, I can see that my hydrogens physically don't interact on the same space. And on the molecular level, there are electrical charges that are preventing this overlap as well. But they don't just interact physically. It's like having a bunch of little magnets all trying to move around each other. And so just being able to turn and rotate these molecules will cause themselves to have more tension. So when we look at diastereomers, we're going to look at geometric isomers that are physically unable to shift their position, and we're going to look at conformational isomers, which will move around, but as they move around, they will cause more tension, more torsion, more forces trying to pull the molecule apart. There will be more stable conformations, there will be less stable conformations. We need to be able to understand these. Okay? So that's the introduction to isomerism. We're next going to get into some specific naming traits for our cis and trans molecules.